get all of. Cool. Can you guys all access the Q&A? Maybe just one person or two people just say something in there so I can make sure it's working. Awesome. Perfect. Thank you, guys. All right. Well, we might wait one more minute until starting just to give people some time to join the Zoom. But otherwise, we will make a start on nomenclature in just a second. Cool. So I think you guys should be able to see my screen as well by now with the presentation and everything up. Actually, we might just make a start given that the last one went a little bit over time. So welcome everyone. Getting pretty close to exams for a lot of you, especially those of you who are studying HSC, but also, you know, VCE, QCE kids as well. Hopefully today you'll learn a little bit and do a bit of revision regarding how to name organic compounds. A little bit of info is that we should be able to finish on time, I hope, for this presentation. Maybe a bit of question time at the end. If you guys have any questions you want to go over, you can drop them in the Q&A. And as we go through, I will take a look. But also, if you have any questions that are maybe a little more useful to be answered later, then I will save them for the end of the presentation to go over them. If you guys are looking for a tutor or any help with your preparation for exams, scan the QR code. You'll find some really great free as well as private tutoring resources. There's a lot of things that you guys can access on our website, including the previous lecture and a bunch of other online resources. And a little bit of info about me is my name's Manoj. I graduated back in 2016 from high school, which seems like a lifetime ago, and I studied with VCE. I'd got a perfect score in VCE chemistry, and I've been tutoring chem to students all across Australia from different curriculums for almost 6 years now. And I'm in my final year of the medicine program at Monash Uni. It's been 6 years of uni, massive slog, but I'm very excited to almost be done. And hopefully you guys are excited to almost be done with your 6 years of high school. So without further ado, let's take a look at what we're going to be covering. So we're really going to be focusing on two key concepts: getting good at naming, which is really relevant to organic chemistry, and then bonding, which is also arguably more important to organic chemistry. These are probably the two most important things that you need to get really good at for anything to do with organic chem. But I think if we've been able to cover them by the end of the lecture, you'll be in pretty good standing. So when covering stuff to do with naming organic molecules and nomenclature, the requirements vary by curriculum. HSC, VCE, QCE, SACE, WACE, etc., all have slightly different requirements. But these types of functional groups and compounds, pretty much every curriculum needs to know. So I will mainly focus on them. Now, I don't have time to go over each of them in detail, but what I will do is focus on kind of the important aspects of each one. So let's introduce nomenclature by going over some of the foundational concepts. Nomenclature of organic compounds exists because scientists are lazy. They wanted to work out an easy way to share information and let other scientists know what type of chemical compounds they were talking about, which is why the Iupac system exists. This is an international system used by chemists all across the world in order to name organic compounds. Now, scientists essentially devised this system to figure out a way in which they can provide you with the least amount of words and information needed, so that if you were to give someone else the name of this compound, they would be able to draw it exactly how they wanted you to. So it's a very efficient naming system and a very accurate naming system. It provides the least amount of info required for you to get the most out of the name. Now, one key thing to remember as we go forwards, very basic, but just keep in mind that carbons have 4 bonds. So they can either have 4 single bonds, they can get rid or kind of join 2 bonds to make a double bond. They can do that twice if they want to. They can also have a triple bond and a single bond. But overall, we need to add bonds up to 4 bonds per carbon. Just a bit of background knowledge that'll be useful and important. So let's make a start on how nomenclature works. Given that I only have half an hour, less than half an hour now to go over this stuff, I'm not going to go over each of the functional groups in too much detail because hopefully by this point of the year, you know what a carboxy group looks like or what an alcohol looks like. What I see my students and most students at this point of the year make mistakes in is they've kind of just forgotten a bit about the general principles and structure about how to name an organic compound if I was to just put one in front of you. So we're going to focus on the general rules that apply to all organic compounds, regardless of functional groups, regardless of what kind of components make them up. We're going to focus on the general principles. So first things first is this is what our general structure of a name looks like. And as you can see, it's comprised of 4 main parts. We've got our groups at the front. We've got our chain or our chain length. We've got a bit of info about the bonding. And we've got our suffix at the end. These 4 components pretty much make up all the names that you need to know. Now, when it comes to actually constructing these names, I suggest you start with the chain component as it is the easiest to use. So start off with the chain component when you're naming, as it's the easiest place to start. Essentially, when it comes to the chain component, what we're talking about is trying to find the longest carbon chain. And we'll do an example to see this in action a bit later, but the chain component is finding the longest carbon chain. And then what we do is we number it from the most important side. So step number 1 is identify the longest carbon chain. Step 2 is to number it. And step 3 is to name it. And we'll name our carbon chain meth, F, prop, but, etc., depending on how many carbons there are in it. So as way of an example, in this case, but would be the chain component for this name, whereby we're referring to the number of carbons in the longest carbon chain for this molecule. So remember, your chain is the easiest place to start if you need to name something, write out the chain first. What you want to do next is go for your bonding. That's the second place that you should go. Now, bonding is relatively easy to identify. You look at the longest carbon chain, and you simply work out whether there are any double or triple bonds in that longest carbon chain. And then you will change your kind of second part after the chain, depending on if there are other types of bonds present. If it's all single bonds, then you will use AN, ane. If there are double bonds present, like in this example, you will use EN. If there are triple bonds present, you will use YN. These are the main variations when it comes to bonding. So what you need to do is after identifying, after numbering and naming the longest carbon chain, is to look in that long carbon chain and work out if there are any double or triple bonds. And the way we number them or we name them, so for example, in this case, the 3, is we use the lowest number. So this is a bond between carbons 3 and 4 in the chain. So we always use the lower number in our name. We don't use a 4 if it's between carbons 3 and 4. We use this one. So that's a bit of an overview of how we go about our bonding. Now, if there are none, we just go with ane. If there's a double bond, we use ene. If there's a triple bond, we use ine. And I usually like to just write the first 2 letters because usually while there's an E at the end of all of these, you will usually need to remove it if there's a suffix. In this case, we've got an ol for an alcohol. So we've removed the second kind of like vowel here and replaced it with the suffix. So that's a general overview of our chain, step number 1, and then bonding. Now, when it comes to our groups and our bonding and our suffixes, we need to make sure we follow kind of a substructure or a mini structure within it. And this doesn't apply to our chain. As I said, it just applies to our bonding, our suffix, and our groups, as we can see here. The way we do it is we kind of organize it in these sections. We use numbers with commas to indicate where on our longest carbon chain these things exist. Then we have a hyphen. So 1, 1 is our numbers with commas, and we have a hyphen. Then we have a prefix depending on how many things there are. So in this case, we've got 1, 1 indicating we've got 2 of a specific functional group. And we then use di. And this di prefix indicates that there's 2 of something. Now these prefixes, if there's 1 of something, there's no prefix. There's 2, it's di. 3 is tri. 4 is tetra, 5 is penta. And these are the prefixes we use when there are multiple functional groups, multiple double triple bonds, or multiple suffixes. Then we use the actual name. So in this case, it's fluoro because there's a fluorine present. That's how we go about numbering and naming the kind of individual sections within our groups, our bonding, and suffixes. So this is a quick overview of the structure. The last thing that I'd like to do is just quickly overview the suffix and the groups, because I haven't really gone over them in too much detail. So the way that I like to go about it is, number one, obviously understand the structure that we've just gone over, numbers with commas, hyphen, prefix, name. Now, after going over our chain and our bonding, which we did first, I like to move on to the suffix next. Now, what do I mean by a suffix? So the way that I like to think about a suffix is that it's the last part of a name. And if you think about if you've ever been on the school bus, there's like a very clear hierarchy on the school bus. Everyone at school wants to sit at the back seat, but the most important kids, usually the year 12s, will sit at the back seat of the school bus. And it's kind of a similar hierarchy here. The most important functional group or section of a molecule will get the name at the suffix. So for example, the main ones that we really see are carboxy groups, hydroxy or alcohol groups, and amine groups. All of these 3 groups have suffixes. For carboxyl groups, it's oic acid. For hydroxyl or alcohol groups, it's an ol. And for amines, it's something amine. They go at the back, but only the most important one can sit at the back of the bus. So in this case, if we have multiple of these present, for example, if we have 1 carboxy, 1 hydroxy, and 1 amine present, only the most important, the carboxy, will get the position of the suffix. So I like to use the suffix next. So we go chain first, then bonding, and then the suffix. And remember, the most important one gets the position of the suffix. And this is your hierarchy: carboxy, alcohol, amine. Finally, for everything else present in our molecule, we put them at the start. So any remaining groups, and then everything else like halogens, etc., and any branches all go at the start. Once again, following this structure: numbers with commas, hyphen, prefix, name. So the way that I go about it is I label any functional groups present in the molecule. I list them at the start in alphabetical order. So for example, if we had a methyl group, we would go fluoro first and then the methyl group to make sure we're being in alphabetical order. Then we go number, commas, hyphens, prefix, name as the kind of naming structure. And in general, just remember that if you're not too sure, our commas go between 2 numbers. So if we're splitting up 2 numbers, we always use a comma. If we're splitting up a number and a letter, always use a hyphen. So that's kind of the naming structure. So to recap, when naming stuff, start off with your carbon chain, find your longest carbon chain. Then take a look at the bonding present. If there's any important groups, put the most important group at the back. And then finally, put everything else at the front, all your other functional groups. That's a quick overview of how our bonding works in general. Now what we'll do next is let's try drawing this and naming it. So it'll be a little bit easier if we kind of work forwards and backwards. So 1,1-difluoro-but-3-N2-ol. Let's try and draw what this looks like and then kind of reason as to why this is a name. So but, so me, a scientist has told me that this is a name of a molecule, and this should tell me all the information I need to know in order to name and draw this structure. So what we'll do is start with the chain again. But indicates that there's 4 carbons in the chain. Next, the bonding. So let's say that this is carbon 1, 2, 3, and 4. As we can see, we have a double bond indicated by the En, and that's on carbon 3. So we always start with the lower number, carbon 3, and go to carbon 4. There's our double bond. Next, we move on to the suffix. We've got an alcohol group here, and it's located on carbon 2, as noted by the 2 here. So we've got an OH. And then going all the way to the front, we've got 1,1-difluoro. So we've got 2 fluorine groups, and they're both located on carbon 1. So we will go 1,1-difluoro. And there we have most of our molecule. Everything else is just filling in the H's and making sure your carbons have 4 bonds. So this is 3. We'll add another for the H, add another one here for H. This one's already got 3. We'll add 1 over here, and we'll add 2 over here. And there we have it. There's our molecule. Now let's work backwards and explain the name once again. So let's say that we've got this molecule that's been given to us, and now we need to name it and work out what its name is going to be. So start with the chain. We've got a carbon chain that is shown to us over here. And there's only one main carbon chain. Whoops. We don't have any branches. So here's our carbon chain. No branches present. It's got 4 carbons. This is our longest carbon chain. And we're going to number it from the most important side. Now, in this case, the most important side is the left, because this is where our OH group is, and that's considered the most important group. So we number it carbon 1. Sorry, I keep selecting highlighter. 1, 2, 3, and 4. So 4 carbons in our longest carbon chain. We know it's going to be but. Now, are there any double bonds present? Well, yes, we can see a double bond present between 3 and 4. Now we need to remember our double bonds, when naming them, we use the smaller number. So it's going to be but 3 as our number. There's only one of them. We don't need any commas. We've got a hyphen here. We don't need any prefixes because there's one. And because it's a double bond, we're going to use N. And there'll probably be a little bit more here. I'll leave this blank for now. We'll move on to the suffix. Now, do we have a carboxy group, an alcohol group, or an amine group? Yes, we do. And this is located on carbon 2. There's only 1. So we're going to go 2. Don't need a prefix because there's only 1. Ol. And now what's left in terms of functional groups? We've ticked this one off, tick this one off. Here we have our 2 fluorines. So we're going to go 1, 1, because they're both located on carbon 1. And just because they're both located on carbon 1 doesn't mean you can only give one number. If there are 3 fluorines, you need to have, 3 numbers in front. So the number of functional groups should always be the same as the number of numbers in front here. So 2 of fluorines means 1, 1. Because there's 2, we need to use di as a prefix, then the name fluoro. And there we have our full name, 1,1-difluoro-but-3-N2-ol. Bit of a mouthful, but it should be correct. I'm just going to check if there's any questions. Looks like you guys are all following fine, so I'll leave it there for now. And let's do a little bit of practice. I'll give you guys maybe a 30-second head start to try and name this molecule. So just starting a timer, and then I actually haven't seen this molecule before. I just drew it randomly, so I will try and name it next. So remember, step number 1 is a chain, followed by bonding, followed by the suffix, followed by the groups. I'll give you guys another 10 seconds. All right. So 30 seconds is up. If any of you work it out, you're welcome to type it into the chat. I'm going to start explaining how to name this. So first thing is to identify the longest carbon chain. And as you can see, we've got carbon chain happening here. We've got two pathways, this one and this one. We want to go with the longest one. So we're going to select the longer of the two chains. This is going to be our main carbon chain. Now we want to also number it. So we're going to number it from the most important side. In this case, the left looks pretty boring. The right-hand side has an OH group. Means it's pretty important. We're going to go 1, 2, 1, 2, 3, 4, 5, 6. We've numbered our carbon chain as well. So it's got 6 carbons. We can name it as being hex. Now let's move on. We've ticked off checkpoint number 1. Move on to checkpoint number 2. Are there any double bonds here? Are there any triple bonds here? Looks like things are very, very plain, so we don't need to worry about them. We're just going to have an ane. So AN, I'm going to skip the E for now, just in case there's a suffix. Step 2 is now done. Let's take a look at whether there's a suffix or not. So step 3. Is there a carboxy group, an alcohol group, or an amine group? Yes, there is over here. So our OH group is attached to the first carbon. So hex and 1-ol. Don't need a prefix, don't need any commas. There's only one OH group that I've seen. So that's our suffix ticked off. Now everything else we need to do in our kind of start of a name with our groups. We've got 2 fluorines over here and we've got a methyl group over here. It's a methyl group because there's only 1 carbon in this branch. So we're going to name them in alphabetical order, F for fluorine first, and then M for methyl afterwards. Here we've got 1,1-difluoro. Because we've got 2 fluoros, we need 2 numbers as well as a di. 1,1-difluoro. Now we're going to use a hyphen because we're going to have some numbers after letters. And we're going to say 3, again, another hyphen, methyl, for the methyl group, hexane 1-ol. Now, as I said, I haven't seen this question before. This could be wrong, but I'm pretty sure it's correct. 1,1-difluoro, 3-methyl hexane 1-ol. That's the name for this compound. Now, let's do one more example. I will again give you maybe just a 15-second head start because we are running low on time. All right, 10 seconds. Cool. Let's take a look. Once again, exact same structure, exact same process. I'll move a bit faster this time, starting off with our chain as number 1. So let's take a look at the chain. Can we find the longest carbon chain? It looks like there's only 1 carbon chain for us to worry about here. And it seems like there's no other branches. So we're just going to go with that as our carbon chain. Now we want to number it from the most important side. What important things are present? We can see that there's some hydroxy groups, some double bonds, and a carboxylic acid group. This is going to be the most important. So we number it right to left. 1, 2, 3, 4, 5. And this is going to be a pent. So we've just ticked off our chain. Now what we do is take a look at a bonding. We've got a double bond present over here between carbons 2 and 3. So remember, we want to use the smallest number, number 2. Pent, 2, any others present? No, just the 1. So pent 2N for the double bond. And then probably have a suffix afterwards. We definitely have a suffix afterwards because we've got some things that are present. We've got carboxy groups. We've got the one carboxy group here, and we've got two alcohols over here. Now think about your hierarchy: carboxylic acids, alcohols, amines. We want to use the most important one. The most important one sits at the back of the bus where our suffixes go. So we take our carboxylic acid. And in this case, we could say 1-oic acid. Now that's our suffix. And finally, we move to our groups. It seems like the only real group present is the hydroxy groups, and there's two. So we're going to go 4,4, because they're both on 4, dihydroxy, and 2-enoic acid. Now, just a quick note, our carboxylic acids are by default the first numbered, the first carbon in the carbon chain. So we don't necessarily need to include the 1-oic acid. You can if you'd like to. Most curriculums won't mark you down for including it. It's a little bit of extra information, but it's not incorrect. So you could say this, and I doubt your curriculum would mark you down, but please make sure to check because it does vary a bit state by state in Australia. So this is our final answer: 4,4-dihydroxy pent-2-N-oic acid. All right, quick summary, guys. Step number 1, find the longest carbon chain and number from the most important side. Name your double and triple bonds. Use your suffix, that's the most important. And then finally, label all the other groups in front. Now, in the last few minutes, we're very quickly going to go over bonding. Bonding is probably the most important topic when it comes to organic chemistry, and I really recommend you guys revise it. Questions in exams tend to be about things related to bonding. Questions about boiling point, melting point, flash point, viscosity, denaturing enzymes, surface tension, solubility, it goes on and on. All of them, when answering questions, especially short answer questions about them, need to be about bonding. So really make sure that you have a good grasp of bonding. I'm not going to spend too much time because this is a lot of different kind of examples, but we'll just quickly categorize our bonding and get a very brief overview. There's two main types of bonding: intramolecular and intermolecular. Intra means within, so it's within molecules. Inter means between. It's between different molecules. Now, intramolecular bonds are your things like covalent bonds, your ionic bonds, and your metallic bonds. For most of you in year 12, these won't be super important in terms of the questions that will get asked. You should know them. I recommend you revise them, but they aren't going to be as common as questions that have to do with intermolecular bonds. Intermolecular bonds are things such as dispersion forces, dipole-dipole bonds, a subset of which is your hydrogen bonds, and then things like your ion dipole bonds. These are weaker than intramolecular bonds. Intramolecular bonds in general are super, super strong, and you don't need to worry about them too much because, as I said, they don't come up in questions as much in year 12. Should know them, but I won't cover them right now. Intermolecular bonds are between molecules, and they're important. You've got dispersion, dipole-dipole, and ion dipole. Dispersion forces exist between all molecules. Dipole-dipole and ion dipole are very much to do with polar molecules. In general, H bonds have to do with substances that contain nitrogen, oxygen, and fluorine. These are the ones that molecules will be able to form hydrogen bonds with. Nitrogen, oxygen, fluorine, when they're present, allow H bonds to form. Now, in most of your questions, things will often be related to temperature. So I'm very quickly going to go over an example. Here we have methane. Methane is a non-polar molecule. It doesn't have any polar groups. It can only form weak dispersion forces because, as we said, weak dispersion forces are present between all molecules. So it will have dispersion forces between all of its different atoms. And these will be very weak attractions. In contrast, methanol has an OH group, which means that it is polar. Thus, it is able to form hydrogen bonds, and hydrogen bonds are much, much stronger than dispersion forces. So we're able to form links that are much, much stronger between the molecules. Now, the key thing to remember is that this is directly proportional to a lot of our characteristics: boiling point, flash point, etc., etc., etc. If we have stronger bonds, this means we have a higher temperature for our boiling point. We also have a higher temperature then for our melting point. Our flash point, the point at which we have sufficient vapor to ignite, is also going to be a higher temperature. Stronger bonds means our molecules kind of cling to each other more tightly, which means that it takes more energy, specifically heat energy. So let's say that we add some heat energy. So we add a lot of heat energy underneath here. Pretend that's fire. It doesn't look like fire, but it'll have to do. And what we cause with heat energy is we cause movement. So think about it like this. If you have these molecules and you start to light a fire between them, they start to run around like crazy. And this is what we call kinetic energy. They start to vibrate, they start to move around, they start to really just kind of speed about depending on how hot it is. And this happens to both molecules. Now imagine if you and a friend were just running about randomly or spinning or doing something along those lines, and a couple of you had, I don't know, something like maybe like the two of you were holding a jelly snake versus the two of you were holding a chain. Eventually, the jelly snake would break. And that's what happens when you have a lot of movement and weak bonds. Eventually, these bonds break at a lower temperature, even if they're not moving about too much. Whereas stronger bonds require higher temperatures, higher energy, more movement in order to break. Just like when you're holding a chain, it takes a lot more energy to break a chain. And so when it comes to things like viscosity, our molecules are clinging to each other stronger, their intermolecular bonds are stronger, we have more viscosity and slower flow. Stronger bonds means that enzymes have a higher temperature at which they denature. It means that our surface tension is stronger, and it means we have more solubility. So if I can recommend one thing for you guys to really revise, hopefully at this point, you'll have a decent understanding of nomenclature. Really spend a lot of time going over bonding, intermolecular bonding, especially that exists between molecules. And remember that it has a lot to do with temperature and kinetic energy. As temperature and kinetic energy go up, the bonds will start to weaken because they're being yanked around everywhere, and only the strong bonds will last longer and thus require higher temperatures before they break. That's all for today, guys. Hope that all made a lot of sense. If you've got any questions, I will stay back for another minute or two to answer them. But otherwise, I would really recommend, if you need a bit more help with your chem preparation and revision, scan the QR code. If you need a tutor, go for it, grab a tutor or join a group class in the preparation for your final exams. Or you can also sign up for a 7-day free trial of our online programs. They'll give you access to a bunch of videos that go over lots of content like this in really short, kind of digestible videos, shorter than this presentation. And you'll be able to revise your concepts really quickly before exams. That's all from me. I'll give you guys like a minute or so for any other questions in the chat. Otherwise, thank you for attending, and I hope that was useful. I'll give you a second if you have any questions. All right. Seems like pretty much everything has been answered. I think we'll leave it there, guys. Thanks very much for your time and enjoy the rest of your weekends. See ya.